In the previous sections, we have discussed electro-optic effect and we discussed various aspects in terms of the basic physics, the configuration and different modulation schemes of electro-optic devices. And now, we will discuss another very promising aspect, that is this acousto-optic effect, the light matter interaction through acoustic waves in the host of material medium. The acousto-optic effect, it basically consists of the interaction of the acoustic wave with the light wave through a medium, where the medium will be deformed by the acoustic wave which is travelling through it. We know that when there is an acoustic wave, it creates a compression and rarefaction in the medium, and the places where which is periodic and periodic with the frequency of the acoustic wave, and the places where it is compressed and the places where it is rarefied, this the compression and rarefaction zones, the material undergoes deformation of two different types. But this is a phenomenon which is which should happen even when there is a static strain. If there is a force on a medium, then the medium the bulk of the medium will undergo some deformation, and this deformation will create in turn some strain. The strain will be inducing, will be creating some changes in the optical properties in terms of the permittivity and the refractive indices of the material. So, we will discuss this acousto-optic effect initially with the elastic deformation, which is the foundation to understand how this interaction takes place. We will study this elastic deformation in terms of the infinitesimal strain. The strain, we will see that it is composed of normal strain and shear strain. Then there will be a strain and rotation matrix, which is there in the case of a deformation of any material medium. Then we will pick up this polarization optics, polarization of the acoustic waves, then the acoustic waves in an isotropic and anisotropic medium, pure and quasi transverse and longitudinal modes, and the degenerate modes. So, first is to understand this elastic deformation. So, any elastic deformation and corresponding mechanical strain modifies the optical properties of a medium. This strain, this deformation, which could be fixed or which could be time varying, will create a strain in the medium, whether the medium is isotropic and anisotropic. Because of the strain, there will be change in the optical properties. This fact is the photoelastic effect, that is the modification of the optical properties as a result of the elastic deformation. Now, when this elastic deformation that produces strain, it could happen by a travelling acoustic wave. As the wave travels through the medium, there will be a periodic compression and rarefaction in the medium. That means, there will be a periodic deformation in the medium, and because of the periodic deformation, there will be a periodic strain in the medium through which this acoustic wave is travelling. Because of this periodic strain, there will be periodic changes in the permittivity properties of the medium, which will be manifested in terms of the changes in the periodic changes in the refractive indices in the medium, which will result in a periodic refractive index grating. That means, when an acoustic wave is travelling through a medium, because of the dynamic photoelastic property, there will be periodic deformation, periodic strain and periodic changes in the permittivity, periodic changes in the refractive indices, and therefore, there will be a formation of periodic grating as long as the acoustic wave is travelling through the medium. Now, if a light wave is passing through such a medium, this wave will see a dynamic periodic refractive index grating, and as a result this light wave will be diffracted. This effect we will call this Acousto-optic effect, that is the changes in the optical properties by an acoustic wave travelling through a medium, whether the medium is isotropic or anisotropic. This effect is always there. We will study the effect in the case of isotropic medium and anisotropic medium, and in terms of various configurations of the acoustic wave through the medium, whether it is a longitudinal wave or it is a shear wave, we will study those cases. But by now we realize that it is important to understand the elastic deformation and how they are connected to the changes in the optical properties through a change in the permittivity of the medium. Periodic change in the permittivity of the medium when it is associated with an acoustic wave, with a mechanical wave travelling through the medium. But otherwise, for a static deformation, we will see how this deformation is related to strain and how the strain is related to the modification of the permittivity properties. So, elastic deformation. Let us first consider the deformation of an element within the volume of a medium. Let us suppose that this is the original undeformed state of an element. There are 2 points P and Q, whose coordinates with respect to this lab frame is given by this r 0 and r 0 plus d r 0. Now, under deformation it moves to this place. This is the deformed element, where the point P has moved to P dash and the point Q has moved to Q dash, and the resulting separation is now d r dash. So, this is the original element and this is the deformed element. Now, let us see that this coordinate of P dash is now r 0 plus u r 0, a function of u a function of r 0, whereas the coordinate of q dash is originally it was r 0 plus d r 0. So, u as a function of r 0 plus d r 0 will be the new position characterized by this position. So, the deformed separation between these 2 points, the original separation between P and Q was d r 0, but the separation under deformation is d r dash, which is just the difference of these two. So, we can write r 0 plus d r 0, then minus of this quantity. So, therefore, we can write this equation, because this u of r 0, u of r 0. So, that they will cancel, these two will cancel, and this will be the q dash minus p dash. If you do, you will obtain this equation, which is to define the separation between p dash and q dash, the deformed separation, the separation between the points under deformation. So, d r dash, that separation is equal to this. We will use this Taylor expansion of this. Now, these two terms will be cancelled. So, u r 0 plus d r 0 can be expanded in the Taylor series. So, if you return up to only 3 terms up to d x 3, we can write this d r 0 as a function of d x 1, d x 2, d x 3. Then we can expand this in this form. this dr0, if we write as a function of these dx1, dx2 and dx3, these coordinates, we can expand in this form. So, this expansion can be written in the compact form, retaining up to 3 terms, that u of r 0 plus d r 0 equal to u I r 0 plus this, and then sum of these terms. In the vector notation, we can write this connection as u r 0 and then del u dot d r 0, where this del u, we know that it is the displacement del u y del x j. So, where I and j can take up values up to 1 to 3, and this gives you this matrix, which is a tensor and a tensor of rank 2 or is also a dyad. So, this is the del u, this quantity, which is represented by this. You can look at the diagonal elements del u 1 deformation along the same direction, deformation along the same direction. So, the force, the strain, that is along the applied stress, applied force. So, we will see how it works. So, in the vicinity of P, in the vicinity of P, we are to find, we want to find the separation, the change in the length of the segment P q. So, we started with a length P q, and now under deformation it has gone to P dash and Q dash. So, now you would like to know how much is the change that this P q element has suffered when it has become P dash and Q dash. So, P dash and Q dash, P dash Q dash minus P q will be the change, and now this dr dash can be represented as this we have seen, this we have seen. So, this is the effective element, therefore, dr dash, which can be written as this quantity, which can be written as this dr 0 plus du I dj dxj. This also we have seen here, dr 0, this quantity. Okay. So, now that change in the length P q, that is P dash Q dash minus P q, will be dr dash minus dr 0. Therefore, in a compact notation we can write that this is equal to du I dj dxj. So, this is the change, and the change per unit length will define the strain. So, if we divide this by dxj, so this change has occurred for a length over a length of dxj. So, if I divide this by dxj like this, then it gives you the deformation, that is du I. So, change in the length per unit length will be du I by dj, which is the deformation. So, we arrive at this, that we have a deformation which is del u I del x j, where I and j can take up 1 to 3 values, which will give you all 9 elements deformation, y with respect to x, x with respect to y, z with respect to x, and so on. So, that can be put in this form del u 1 del x 1. So, this is the deformation tensor, which can be written in the form of 2 matrices. I retain the diagonal elements as it is, but it can also be written in this form, half of del u 1 del x 1 plus del u 1 and del x 2 again. So, that sum of the 2 elements, half of that twice, we can write in this form. So, these diagonal elements will be 0 in the case of the secondary matrix, and if I write this off diagonal elements in this form, so the sum of these two will be the same as it is, will be the same as the off diagonal elements. And so, we can write this deformation matrix as a sum of 2 matrices, and let us see what does this matrix indicate and what does this matrix represent. Okay. So, this is you can see that del u 1 del x 1, this will define the strain, because if you apply if there is a change in the length in the same direction per unit length, that will define the normal strain. This will be the normal strain, whereas this quantity del u 1 del x 2 plus del u 2 del x 1 will define the shear strain. So, first matrix, this one will be the, it corresponds to the strain tensor, whereas this one del u 1 del x 2 minus del u 2 del x 1 and so on will represent a rotation tensor. Therefore, we find that any deformation can be expressed as a combination, as a sum of a strain tensor as well as a rotation tensor. We will try to understand how these terms represent rotation and these terms represent strain. So, any deformation is the sum of a strain tensor and a rotation tensor, where this S I j stands for infinitesimal strain. If I equal to j, then we get the diagonal elements, I and j are the same. So, this will represent the normal strain, and if they are different, then we get the shear strain, that is this tangential strain, which are represented by these off diagonal elements. And for this R I j, this will be the elements of the rotation tensor. We will see that this is antisymmetric, because theta x will be in the off diagonal positions, it will be minus theta x. So, the deformation can be expressed as this strain infinitesimal strain tensor and an infinitesimal rotation tensor. They are represented by these two tensors, these two matrices. The infinitesimal strain tensor has 6 independent components. We have seen they have 6 independent components. Out of them, these 3 diagonal components, the 3 diagonal components S 11, S 22 and S 3, they are the normal, and tensile strain, it represents the strain along the same direction, whereas it represents the strain along the perpendicular directions 1 2, 2 3 and 3 1. So, the strain in the tangential direction is represented by these off diagonal elements. For the case of rotation tensor, R 11, R 22, R 33, that is the diagonal elements are always 0, but there will be 3 independent components R 1, 2, 2, 3 and 3 1. We will see they are antisymmetric in nature. So, these are the normal strain, these are the shear strain elements of the strain matrix. For the rotation matrix, these are the 3 independent elements 2 1 1 2, 3 1 1 3, 2 3 3 2. So, these are the shear elements. Now, let us understand how it represents the rotation matrix. To understand that, let us consider any vector, and the rotation operation is nothing but taking the curl of this vector, and the property that is required, that this vector A has to be differentiable everywhere within the field where we are looking for the rotation. So, any rotation of a vector, if we take this vector, if we give a translation of this vector from here to here, or from here to here, from here to here and from here to here, the colors represent the positions, they are parallel translation. So, being along the spoke, this rotation of the vector is nothing but being at the periphery of the rotation of the circumference the vectors lying. So, these two are identical situation, these two are the same thing. So, all the vectors can be picked up and placed at the periphery, and they will look like this. So, this is the rotation of the vector. A point A moves from A to B, a point A moves from A to B is nothing but this vector, this has undergone a change in its position from here to here. A vector moves from this A to B, and from B to C is nothing but this vector has gone to this position and then in turn it has gone to this position. So, now we can change the we can look at the change in the position of these two vectors. So, it is like the rotation of a disk and as shown the stages in the figure, one can give a translation of the vector from the periphery to the center or from the center to the periphery as well. That gives you the new rotation visualization. This rotation of the vector can be thought of the rotation of the vector like this. So, therefore, this rotation of A by any amount theta can be obtained by taking the curl of this. So, del of A is equal to 2 theta, this we know from the elementary differential calculus and mechanics. Then let us take the example, if we take A is equal to displacement vector, then this will be connected with theta S equal to r cross theta cross r and del cross S will give you 2 theta. And similarly, if you take this A as the velocity vector, then V equal to omega cross r, which will give you del cross B equal to twice omega. That means, if you take 2 to this side, omega will be represented by half of del cross V, and likewise if we take theta on this side and this 2 to this side. So, half of del cross S will represent this theta. So, any rotation theta will be represented by half of this curl of this displacement vector. So, this is the point that is connected to the elements of the rotation matrix. Therefore, half of del cross S is equal to theta. If I now write it component wise, then the rotation about x in y z plane by an amount theta x can be represented by, look at this, if I take the x component of theta, then I will have to take the x component of this quantity, which will be del s z del y minus del s y del z. So, this is your theta x, but if we take del s y del z minus this, then this will represent minus theta x. Similarly, theta y is this, the y component of this vector on either side will give me this quantity, z component of this vector on either side will give me. So, I have been able to see that this rotation theta x is nothing but this displacement of the displacement components of the displacement vector along different directions and their differences. So, therefore, this rotation tensor elements R I j can be written as half of del S I del x j. You can see that I and j can take up 1, 2, 3 these 3 values. So, it correctly represents the rotation of this vector. Therefore, these elements are the R I j and R j I. You have to just flip this minus this, and as a result this R x y and R y x, they are not same, there will be a minus sign. R x z and R z x, they are not same, there will be a minus sign. Therefore, this rotation matrix is always an antisymmetric matrix. So, this antisymmetric, the R I j a deformation by rotation. To visualize that, to obtain that, one has to apply a torque or unlike parallel force of equal magnitude, which will create a rotation, and a deformation that occurs by translation. To get that, one has to apply a force along the Cartesian axis. So, a torque is required to create a rotation, and a translation, a linear force is to be applied along the Cartesian axis to get the. But in the case of deformation, both the things are coming into play, and any deformation is a sum of these two things, that is the strain and the rotation, which could be represented as the sum of the two tensors, the strain tensor and the rotation tensor. And now, we will see the deformation that is induced, that is created in a material medium when the acoustic wave is travelling through it. So, this was first observed, light scattering by acoustic wave by Brillouin, and that is Brillouin scattering, and Acoustic frequencies involve ultrasonic and hypersonic waves, that is caused by thermal excitation in the medium. The study of acousto-optic effect is usually by ultrasonic waves are used within the frequency of 100 hertz to a few gigahertz. So, this is the range of study of this acousto-optic effect. Now, elastic waves in matter for a given direction of propagation r in a medium, any plane wave, travelling plane acoustic wave can be represented by this. We have seen that this represents the phase of the wave, which is a plane wave front k dot r minus omega t. This capital omega is the frequency of the acoustic wave. This should be capital K in the case of acoustic wave. If we want to differentiate from the electromagnetic waves, capital K, which will be the propagation vector, u is the amplitude of the acoustic wave. So, a standing acoustic wave is the superposition of two such forward propagating and backward propagating acoustic waves of the same amplitude. Then we get a standing wave, which is also used to create a standing static type of deformation in the medium, which is also used as a fixed grating, static grating in a medium. When we will see that if we allow the acoustic wave to be reflected back into the same medium in the same direction, the superposition will create a standing wave, and the position where it is compressed and the position where it is rarefied, that will remain fixed with time with position, but not with time. So, that will give rise to a static grating. So, this standing wave is also equally important standing acoustic wave to form a static refractive index grating. Now, this looking at the elastic waves, this property in the matter, there are three orthogonal modes of elastic waves in material medium. The polarization is one mode is polarized along the propagation direction, that is what is called the longitudinal polarization mode. The polarization of the other two modes are perpendicular to the direction of propagation k. So, when there is an acoustic wave, this could lead to a polarization that is along the direction of k, and that is what is called the longitudinal wave. And when the polarization, that is the medium particles, the mechanical vibration of the particles occurs in the perpendicular direction to the direction of propagation k, that is called the shear wave. And this shear wave will be resulting that shear strain, longitudinal wave will result in the longitudinal, the normal strain, that is the usual strain. So, in an isotropic medium and cubic crystals, this normal modes, one is purely longitudinal mode. You can see the medium will be compressed and rarefied along the longitudinal direction. You can see the lengths of the vectors are representing the compression and rarefaction in the medium. So, one purely longitudinal mode, and there could be two purely transverse modes. So, this could be, let us suppose this is directed along x, then there could be y polarization and there could be z polarization as well. So, there are two tangential modes, two transverse modes. These two modes are degenerate, they are identical. So, in an isotropic medium, however, in general the polarizations may not be parallel or perpendicular to k. In general, it may be that the it all depends on the material properties. So, it is very close to longitudinal modes, that is why it is called the quasi longitudinal mode, and whereas this one is more inclined to the transverse tangential polarization. So, this is why it is called quasi transverse polarization. So, this again can have two polarizations, whereas this is the one possible polarization, longitudinal mode. So, at a given acoustic frequency in a medium, the values of V, the velocity of the medium, the periodicity and the propagation vector, they depend on the direction of k, and the all they put together, they decide this polarization. So, in an isotropic medium, you have two transverse modes, two of them are, these two transverse mode are degenerate, travel with the same velocity. but transverse modes are not degenerate with the longitudinal modes. So, they are different from the longitudinal mode. In a cubic crystal, the wave propagating along certain directions defined by this direction or by 1 plane making an equal inclination with all the 3 coordinate axes, the 2 transverse modes are degenerate, travel with the same velocity. In an anisotropic crystal, all 3 modes are in general non-degenerate and are distinct. In general, this is true for anisotropic medium because of the natural anisotropy of the medium. So, by this discussion we tried to understand that when an acoustic wave travels through a medium, it deforms the medium, and this deformation will be decided by the polarization of the acoustic wave. It can have longitudinal polarization, it can have the transverse polarization. Transverse polarization can have 2 degenerate modes. So, these are all going to deform the medium periodically, and as a result of that there will be a periodic changes in the mechanical properties, the strain, and as a result there will be a periodic changes in the permittivity and refractive index properties. We will discuss each of the cases in details and try to understand that different configurations of these longitudinal modes, transverse modes, x polarized modes, y polarized modes in the case of isotropic medium, in the case of anisotropic medium, how they are going to change the permittivity properties, periodic permittivity properties in the medium, as long as that particular acoustic wave is existing in the medium. We will try to understand, and then we will apply those deformation, those changes in the periodic refractive index properties to define the various modulation scheme and various devices. So, by this discussion we tried to understand this basic elastic deformation, the mechanical deformation properties in terms of the infinitesimal strain, which this strain is again consists of this normal strain and shear strain. If the displacement we estimate along the change of the length along the same line, same direction, then it is a normal strain, and if it is estimated in the along the perpendicular direction, you apply a force along this direction and there is a change in a perpendicular direction. This all we know with all details, that this is your shear strain. So, both of these are going to constitute this mechanical strain, whereas the rotation matrix, these two strain and rotation matrix, these two put together defines the elastic deformation. Then we discuss this polarization of acoustic waves. There are 2 different polarization modes, longitudinal modes and transverse modes. These transverse modes are also composed of 2 degenerate orthogonal modes. There could be pure and quasi transverse and longitudinal modes. We will continue with this acoustic waves in the medium. Thank you.